or what we need first is a version of the theorem of the sea, or in tropical version, we know we have the BKK theorem. And this quadratical enrichment goes towards chemistry over a field of positive characteristics, right? Oh, sorry. Yeah. So let's start by defining what is this. Definition. Approximate the group of field of characteristics of 2. Is the group completion of the theory given by the periodic forms of the isomorphism. This was a very nice presentation. Mainly, we have a set of generators by the following. So we already know this product A. This is the form that goes from K to K, or since the characteristic is different than 2 and 1 in a ring, this is the same of considered by linear forms. So this is the form that the xy, let's say xy, okay. And then this is non-degenerate if A is not 0. So this is generated by the units of the field, and then we have a set of relations. Namely, we have that the quadratic form generated by A squared is equal to the quadratic form generated by A. So it's straightforward. Then we have that A plus B is equal to the form generated by A plus B plus A plus B. When A and B are units, and A is unit, and A plus minus A, this is the same. And this we will know by H, it's known as the hyperbolic form. And I just want to say that the tensor product of the forms is given by the product of the generators. Okay. So what is the motivation to study geometry over this field? Well, as we see, we can do this construction for an arbitrary field, and then we can counter them. So motivation is the same. Okay, there are several enumerated counts that we have managed to do. So let's start with the example of lines in a cubic surface. So classically, it is known. So it's known that over the complex, so if I have a complex surface in 3 of degree 3, then the number of lines is equal to 27. Then I know that for the reals, well, it is possible to find a surface that has 27 real lines, where all the lines are even defined over the reals. But this is not always the case. It's, as it happens with polynomials in one variable, not all the rules are defined over the real. So we can have less numbers. So we can have 15, right? 7 or 3 lines. And then, well, the people that have studied this problem over the reals, right? We can, if we have a real line contained on a surface, so the residual, so if we consider a plane that intersects this line, right, the residual will be a conic, right? So if we have a degree 3 surface in the center of plane, you're going to get a degree 2 curve. So if it contains a line, it's going to have a residual conic. So studying this conic, we can have these 2 points, right? And then when we vary the plane, we can see that either the 2 points get close to each other or separate from each other, or they can go on different directions, right? So we have 2 types of conic that we can associate, and then when we think of this number of real lines, we actually see that either we get 15 of one and 12 of the other, or 9 and 6. Right. So we have a kind of a signature that we can associate a sign. So if we do a counted sign, then we obtain the value of the district. And then this phenomena actually can be studied over an arbitrary field. And then if we have a perfect field, then we get that the sign, the counted sign, but now when the signs are the greater than the figure of the field, then we obtain 15 times 1 is 12 times 1. Okay.
Unless, can you repeat what the 2 different types are? And
yes.
And this, I don't know.
Yes. So when you have your receiver cubic, and then you consider your 2 points,
Yeah.
and you move your hyperplane, then it can happen that basically your points.
Which hyperplane am I using?
So basically,
I'm intersecting.
Yeah, this
This
is
line
a plane.
lines in a hyperplane, and this you can move. You have like a pencil of hyperplane.
Exactly. Yes.
Yeah.
Yeah. So this is your plane intersect with the surface, and you have the circle. So these 2 points can either move in the same direction.
Okay, so
Right.
it depends on whether they go together.
Yeah.
And which one is which?
Well, that's an exercise.
That's an exercise.
Okay. So the ones that are called elliptic, they go in the same direction, and the one that goes.
Okay, then minus 1 is elliptic. That makes sense. Yeah, and you don't have any fixed points, and that's elliptic, and then.
Yeah.
And then in the general case, I guess it's where the fixed points are. Like that. That's the
Exactly.
definition. Yeah.
Right. So you get this sign. Another example. And then there's one example that interests a lot with tropical geometers. Let's say it's the Gromov meeting. It's a little bit problematic for me, making sure we're the same, right? Yeah. So if we consider the Gromov meeting invariant of P2 and P3, so in the P3, right? So it's here, and then the complex, right? Then this is the first Gromov meeting invariant that is not trivial. All right, we look at rational curves. Through 8 points. Three. Right. So this is known that this is complex numbers. This is 12. Right. And then for the real, there is not. It's not an invariant number. So this is 12 independent. This is independent of the configuration of point, as long as the configuration of point is generic. So if you want to ask this question of the real, then this depends on the configuration of points. And then what happened here is that depending on the configuration, you can have either 12, 10, or 8 real lines. Then there is a way to making this a real invariant. So if we do this, the sign count with the J signs, we can get that this is 10 direct counted 2 plus 1, plus 2 direct counted plus 1, 9 or 1, or 8 and 6. Right? So we get this version invariant that will be real DUA. And then, oh, sorry. And then it's identified. Okay, this was found by Cass and Green, and then Cass, Levinsoma, Green, they found that these environments we can calculate it for every case. So for every case, a perfect field, we can have that this is A times 1 plus 2 times h. Yes. Or yeah, A times 1 plus 2 times. Okay. We can also ask, let's say, here, what happens if the configuration of points, right, is a configuration that is insecure, right? That is real globally, but not real.
Yeah, there's a question in the chat window. Michael, would you like to speak up and just ask it directly, or should I read it out?
Sure. So I cannot quite read what the Grothendieck weight ring for R. Actually, the Gromov-Witten invariant for R. What does it depend on? I just cannot read what's on the.
On the configuration of points, right?
Yes.
Yes. So yeah. So this is when you are considering rational curves of the tree, you fix 8 points, right? So we want to create, and then as long as there are a generic configuration for the complex, this is an invariant. And then for the real, no, it depends on the configuration that you take. You have different amounts of real curves that passes through this form. Yeah.
Thank you.
Is that yeah. Okay. So, but you can also ask for T real points. And as pairs of complex conjugated points. You got a set of real points, and then you got pairs that it's already complex that won't, yeah, your curves won't pass over the real part, but only over the complex part. And then, okay, so in tropical geometry, we got these invariants that interpolates the Gromov-Witten invariants. Okay, with the Bernoulli invariants. This is known as the blood Geshefer of the real configuration and the blood Schroeder invariants, the von Berger invariants. For the case that we have pairs of complex conjugate points. So in that case, let's say already complex and reals, we have that this invariant equals 8 plus Q. This is going to equal Q plus 2 Q inverse, and then plus 8 minus 2S. Yeah, where S is the number of pairs complex conjugate points. So if I have 8 points, then I have up to 4 couples. So then we can see that when we plug, when we specialize we Q equals to 1, then we recover this the complex invariant, and then for Q equal minus 1, then we have the legendary invariant with the reals, and then, well, Kessler so on immediately, and then you find that perfect field. These we can write as the trace or the field of tensions where the pairs of complementary base points are defined. One plus 2h. What I want. And then that's why I wanted to put the trace as an example because it will play a role in our work. Okay. So any questions after this? Okay, so there's a couple of examples of count or has been count. Yes. So we have Pauli, we have lines on a quadratic circle. And then we get the result. I'll just give you the result of K. 1,445 plus 1,000 minus 1. And then it recovers also the complex in the real case. And then we have works of Larsen and Berg on by changes of the party. This is for the reals, and then what we get 16 1. And then there are generalizations of this. So namely, Octopus and Telemann with Chess and Carbonel will be set in the real count, and then Marley counts for now lines in hypersurfaces, sorry. And there's a recent work, but Marvik Payne and Shaw about the dynamics of a tropical party or plane party. I won't summarize. Okay, so that's, I guess, not motivation, one would say. So what we want to present today is the details of this region for the dissociators, right? That's this was your order K. So let's start by considering what we said. So let's consider the following with the model of a feature. So these. Then let's think of section. So we know that the sections of these bundles are polynomials of the D1 and D2. So the zeros of these sections, sigma, for a binary sigma, this is going to coincide with the intersection points of the variety defined by polynomials. And then, well, you know that over the complex and the genericity conditions, then we're going to have that this intersection, the number of zeros of your section, this is D1 times D2. And then this coincide, the degree of the torture has. And I put it like this because this is the way that we want to think to generalize this. And then we're going to make a space over the reals. Questions so far? Where the reals, of course, is variant. Right, so we need to do something to get an invariant of this. So this is going to depend, and for that we can introduce the local index. So we have now if I'm going to see it locally around the point. So we can have an open set in R2, set one that contains a point P, where the section divided F1 and F2 has an isolated 0. Assume that this is an isolated 0. And then under this assumption, then I'm going to have the following situation. I'm going to be here, where I do F that's in this. Now we come to 0. So we have that when I quotient is this ball, that the ball minus P, this is going to be F2, and then F is going to induce a function in the one class of this quotient. So F induces a function from H2 this quotient. Set. So this is going to give me an homomorphism between set and set. So this is rho degree. The reading our index of Fx, and then we have the Poincaré theorem. Which tells that if our section is binary, then the sum over the zeros section of the index, this is an invariant of the vector bubble. So this does not depend on the section. Invariant in the sense that does not depend. What else? And that's what we have. So now what happens for an arbitrary. So we can use this quadratically enrichment. Well, this was proved by McKean. For an arbitrary field, we get that this vector bundle is orientable. And so what that means that the determinant of B times the canonical of the case. So in this case, the canonical of P2, okay, this is a square. So this is the orientability condition. We translate here to one, so B was all of B1 plus all of B2. So in this case, the determinant times the canonical is going to be O of P2 of B1 plus B2 minus 3. Right? And then when this line bundle is a square, so this is a square, B1 plus B2 is minus 3 is even. So I need that B1 plus B2 is false. So if that happens, then we're going to have that we sum the series of the series of the section. Yeah, we can denote now as A1 degree over X section. This is going to be B1 times B2 divided by H. Right? And this is the determinant group. Right? Well, he proved this in general for Pn. So in Pn, if we have this the sum of the I, okay, then the interceptions account the series of generic section. In this case, so let's put it like this. This is going to be the product of the degrees times 2 divided by 2 times H, given that the sum of the degrees has the same parity that n plus 1. Right? So then, any questions? So, okay, this is the introduction. So,
And then the real case, this index is that index that you introduced here.
yes, yeah, this is visualized.
And then the complex is one in the complex.
Yes, yeah, so the complex. So in the complex, so I didn't give that example, but for K equals to C, right? This quadratic form is this product form. And then if you remember that AB squared is the same of A for every mean 0, then this is the same. Course. In that case, I will relate.
Right. Yeah, I guess it's my turn now. First of all, thanks for doing the introduction. Let me erase a little bit. Like it's, I want to keep this theorem. Yeah, so you get a little break. Maybe let me talk a little bit while I erase. So the whole goal now is, well, we have this nice theory now in numerous geometry to do enumerate geometry results and try to prove them over an arbitrary field, and then the value will be in this open grid ring and this introduced. And this contains the complex count, just like here, because you see like everything will be just one, and we'll get the complex count back. And it also contains the real count, for example, the real counts of lines we've seen before, the sign count of 3, where we have these two types of lines. And the question we asked ourselves was the following: well, like tropical geometry can be used very effectively to solve these kinds of problems. So can we also do this in this enriched setup? So can we also use tropical geometry to get some information about the result of the geometric picture? Can we use this language? And so we just took it as like one of the simplest problems we could think of in a numeric geometry. It's like the first problem in the numeric geometry, namely this theorem, and let's make it even simpler. Let's take it over just for curves. And we're lucky already, we have a theorem in broken grid, so we know what we want to get in the end. So, and we have some kind of formula to get it. So this local index, okay, I just erased it. It's really given in terms of the degree, and maybe let me say what this A1 means. That means that we really replace this by something called the A1 degree, and then this gives us something in broken degree. But instead of introducing this, let me rather tell you what the formula for this one here is. So I guess I should do for curves, where goal. So the goal now is do or prove a quadratically enriched version of presume a tropical curve. I guess everyone in the room is more of an expert in tropical geometry than me. I'm very new to this. So you probably have seen presume for tropical curves. I will still recall it very quickly and then tell you how to attack this problem of actually getting the quadratic count. So for tropical curves. And then we've already seen that McKean proved this nice result that if I sum up over all the intersection points of two curves, so now this is not tropical curves yet, but these are algebraic curves, plain algebraic curves of degree, let's say B1 and B2. And if I sum up these local indices, I get the 1 times the 2 divided by 2 times h. So what is the formula for this? It really is the following. You take the determinant of the Jacobian of f1 and f2, evaluate it at your intersection point. So what is f1 and what is f2? So f1 defines my curve c1. F2 defines my curve C2, like this, and you just stick it into brackets. And then you sum up. And this is really a good thing. Let's think of an example what this does. Let's say we have something of degree 2 and something of degree 3. Then for the complex numbers, this just always gives me a 1 because of the relation, and it's just so this. So this will always be a 1, but over the real numbers, what happens, we will either get, we could just take this to be 1 or minus 1. So this would be a signed count, and you've probably seen that if I count this in a signed way, depending on some orientations, I could assign a plus and then the minus here, because I could just orient my curves. We've already seen this orientation condition. So let's walk along this curve in this direction and along this curve in this direction. And the way these two intersect, this intersection is opposite to this, so that's the other sign, and so on and so forth. So I guess here I get the plus again, minus plus minus. So the sum will always be 0 or a multiple of the hyperwidth. But now you can generalize it by just sticking this into brackets, and then I might need to trace now. We've already seen this trace earlier. So this is the residue field of K over K. What is this trace? That's just really means I take my quadratic form from on our residue field. So our residue field, so this is my quadratic form, and I fold it. And I get a quadratic form for K. And this is 1 times the 2 divided by 2. But we also have this really nice algebraic formula, which should be something like the intersection multiplicity. So let's call this enriched intersection multiplicity. When we do something quadratically enriched, one usually puts a tilde. This is a good definition for the enriched intersection multiplicity. And now we want to use this to define the intersection multiplicity at the top of the curve. Okay. So how can we do this? Well, you probably all know this, but soon, because you do tropical geometry, but for me this is rather new. But studying tropical curves is like studying curves over the field of Puzzle series. So let me just very quickly introduce this. I'm sure you know this, but maybe some people appreciate others try to get a little break. So, and also this fixes some of the conventions. So what is this? What are the elements in there? Let's look like this. Where these qi are all rational numbers and have some common divisor.
T to the power Q1, right? Not the other one.
Yeah. This should be, I guess this is a plus. Thank you.
Okay.
Thank you. Thanks. Yeah. And these things. So this is really low. And I guess you all know this, but just to fix conventions, we have a non-Newtonian variation on this. So let's make, I want to use the plus, the max plus construction. So I'll take, what I'll do is send something, an element like this to minus the lowest exponent. And then you know that, well, the variation A times B is the variation A plus the variation B, and the variation of A plus B is more or equal to the max of the variations. And that's exactly the convention that used to be the case. These are my tropical operations. My tropical design. So what is this? Let me also remind you very quickly. I probably know this, but okay. Let me remind you very quickly how to get the tropical curve out of this, because it also illustrates how we later define the intersection multiplicity. So if let's say we have a polynomial over this field of Puzzle series. So the coefficients are in the Puzzle series. So the on top is the number t, x to the I, y to the j. So this is a polynomial. Some finite number of I and j. So this should be a polynomial. So if we want to find some point lying on the curve defined by f, so 0 is polynomial, we have to do the following. So for p, let's say has coordinates x and y, which is t. And the vanishing of just f, and let's say x is like 0, t to the, we just write minus the variation of x, because that's the lowest exponent plus higher order terms. evaluation of y, terms, and t. Then we can see that if I just plug this x and y t in here, and then the maximum of I times the valuation of x plus j times the valuation of y t plus this tilde has to be attained at least twice.
Valuation of energy.
Why is that? Well, you all know this. We plug these into our polynomial and set this equal to 0. And in order to solve for y and 0, we have to have something where t has the same exponent. And if you stare at it, the exponent exists exactly minus this, the lowest exponent. And this gives us a topical curve. Right. Yeah, for example, it's the easiest one. If I have my x plus k of 0 times x plus a 0 plus y. This turns into, we were looking at the max of let's give these names. Let's just call this Q, ij, and by the use of notation, I call this x, and I call this y. Zero, 0, x plus 0, and y plus q 0. And what you get if you look at locus where the maximum is obtained twice, you get something like this. But yeah, you know what it is. So now what do we want to do? We have this nice theorem here of McKean, and this was in the growth of the ring, but it's okay, but I can just base change and go to the field of Fussell series. So my polynomials here, f1 and f2, are polynomials over the field of Fussell series. Then I can compute this and see if I can relate this to something in this picture. Okay, I guess this will.
Does that change the quadratic ring or is it stay the
That's
same?
the very next thing I'm doing.
Right.
So how's the so what is EW? This one. So remember that the generators W were elements of something that looks like this, where A is unit. Also, remember we had the relation that A is A E squared. So when I could also, let's just leave this later and just look at this one unit square. So the question is, what is this? Well, then let's look at an element in the Puzzle series. Let's write it as earlier, like this. So A is A0, T to the Q0, A1, Q1, 4. What I can do now is I can just take out with A0, let's assume A0 is not 0. So otherwise it's hard. Times T to the Q0 plus A1, A0, T to the Q1. And now I claim that this is a square. Let me read this. So this is a square in here. So why is that? Well, I can take the square root. I'm in Puzzle series, so I can take another square root of this. And then I can inductively solve for something that squares to this. You can do it. It's a linear algebra exercise. This is a square. So actually, it's just unit of K. So the algorithmic grid rings have the same generators. Right. Also, this here, this also goes to, you can also check that all the relations are the same. You need to check that this identification respects the relation. Okay. And what I get from these two exercises, you can do by yourself, I get that the growth grid ring K is isomorphic to the growth grid ring of sources. And we only need to care about the initials here. The rest we don't care about. So make this identification. All right. So I guess what we want to do next is what I already said. Following. So what happens to this formula? This multiplicity of the grid of two curves, C1 and C2, defined by my F1 and F2 here, which was I take the trace from the residue field of a residue field section point P is defined with the Poisson series. I trace down Poisson series, so this is the residue field of P. Determinant Jacobian equations. Question. And the answer is, well, this would give me really not so much. Because when I look at, here I have an example somewhere, I guess. Here I have my equation. I want to compute the determinant of the Jacobian of these kind of polynomials of these forms. But when I pass to the tropical curve, I'm only left with this. So I only have the exponent, the lowest exponent of my coefficient here. But I'm completely losing all the coefficients is in here. I only remember the exponent, but you can imagine if I do this, if I want to compute this, this really depends on these a, I, j tilde. This is actually too much information, which we've just seen. We actually only are interested in the initial term. That's what happens. So we really just care about this initial term of our Poisson series. The rest we can forget, but since we're passing to these brackets, so we can always change it by squares, we can forget about everything here, but we still need to remember these initial terms. So, and that. So the problem, the following, we lose the information about coefficients of our defining polynomials. F1 and F2 here. Here. When passing to tropical curves. So there's no way in actually solving this problem just using the classical methods in tropical geometry. You need to do something else. But there's a fix. And this is really defined by work of Miro, who did that for the real case. I already mentioned that this part here is units mod units squared, which we're actually interested in because it's the generators. If I now choose k to be the real numbers, units in R, not units in R squared. I think I already said that orally when I introduced the zoo. But what is this? This is a set of two elements because I can always multiply something by a square, and then if the element I in R, in units of R I started with is a positive number, I get 1, and if it's a negative number, I get -1 if I multiply by the square root of the absolute values. So I can choose this to be positive as well. And Biro, in his work, assigned pluses and minus ones, attached some pluses and minus ones to tropical curves. Well, and what is the general way to generalize this? Well, instead of attaching pluses and minus 1, we attach more, because we can just attach elements of units mod units of squared, which are exactly our initials in our defining polynomials. But I guess that's a good motivation for what I do next. So let's take a break.